Alright, so now we will see in this lecture a balanced binary search tree. As I told you, there are many balanced binary search tree already known to the people working in this area, but this particular balanced binary search tree, which is called the red black tree, is very nice. Actually, it can be easily implemented. That's why I have chosen this particular red black tree to teach you. Now, what is the first I have to tell you what it is. What are the properties of this red black tree? First of all, it's a binary search tree. All the key elements are kept in the same way as the binary search tree is keeping. But at the same time, each edge has a color. Each edge has a color, red or black. Okay. Inside the computer, how would you implement it? You just keep a bit somewhere. So indicate whether it is on or off. You can just say red and black. Alright, I will be calling it as a red black. Now, there are some properties of these red black edges. One property is every edge to a leaf is black. Okay, this time we will be very strict. The leaf means only those pointers. In the last lecture I drew some nodes with boxes. Those are the leaves. Every other node is an internal node. So basically those empty ones are the leaves. So we will assume basically all the internal nodes, all the pointers, the empty nodes are black. Basically it means that is the first property. Second property says no path has two consecutive red edges. We cannot have that. So if you take a path, downward path from the root to any node, on that path or to a leaf, any leaf, on that path there should not be two consecutive red edge. It's not allowed. Third one is every path from a node mu to a leaf has the same number of black edges. So you take a node and from that node to any leaf you can reach. That path on all those leaves will have the same number of black edges, and that is called the black height. So I'm writing it here, that will be called the black height of the node mu, or we will denote this one as BH of mu, black height of mu. So let me just one example I draw. I'm not going to put the key elements, that's not very important, just the structure. So let us draw all the leaves properly so that we don't get confused later. It's a little bit painful to draw all this, but that's all right. Okay, so this is the tree, and I'm going to denote the edges which are red. I can just with this sign. Okay, so this edge is red. I don't want to put colors here. I just denote it like this. Okay, but because putting colors may not be visible to the camera properly. So this is the indication of rayed edges, and I'm going to put this one as red. Now this is a valid red black tree. You see all the three properties are valid. You can check to any leaf, if you take any path, there is no two consecutive rayed edges. Okay, all these are black, these are black. And not only that, suppose just for an example, if you take from the root to any leaf, the total height is same, black height, 1, 2, 3. So everything is 3, every leaf. Here also 1, 2, 3. Because this is red, so black height is 1, 2, 3 from the root. From the root to say this leaf, 1, 2, 3, 1, 2, 3. Everything is fine. So suppose this one, 1, 2, 3. So any leaf from the root has the same black height. Actually, if you take any node, it is has the same black height, then total number of black edges. So this is a valid red black tree. Now you can see the longest path in this tree to any leaf has at most twice the length of the shortest path to any leaf. It has to be, because any shortest path can have all the edges to be black, right? Like this one, this is the shortest, all the edges to be black, and the longest path has to have the same number of black edges, because of third condition. And how many more red edges you can have? At most intersperse them with one red, because two consecutive red is not allowed. So the longest path can have twice the length of the shortest path. Okay, so this is the key point. Here is coming the balancing. Your one path cannot be too much skewed. Your shortest path and longest path, the difference is within a constant factor, and that is the key point why this tree remains to be of order of log n height. Let's see how to prove. So we are going to prove this. How to prove this claim that this tree has height log n. So my claim is a red black tree with n internal nodes has height at most 2 times log n plus 1. I could have said order of log n, but let us be a little bit precise. So what is the proof of it? The proof is very nice actually. First of all, if there are n nodes in the tree, how many leaves are there? Probably you don't know, or you may know it, that if any binary tree has n nodes, it can have n plus 1 leaves. So note that the tree has n plus 1 leaves according to our definition, the leaves. It has to be true. If there are n internal nodes, n plus 1 must be the total number of leaves. For one node there are 2 leaves, it is true. Okay. You can prove it by induction. Okay. Now what you do, you contract the red edges. If there is any red edge, you contract it. You just merge these 2 nodes which is connected by this red edge into one node. So we will be modifying the tree. If we modify this tree, we will get a tree like this. You can verify it. So you just draw all these leaves, okay? I am not going to draw. So once you contract all the red edges, it will look like this. Just merging the 2 nodes which are connected by red edges. So this tree does not have any red edge, only black edges are present. Okay. Now we know from the property. Let us look into this tree. Every leaf has how much depth? has depth. What is the depth of this tree? Every leaf has depth. No, not. I drew this example with 3, but in general it should be the black height. Black height of the original tree. That should be the depth of any leaf because of the third property. So it has, every leaf has height BH of root. Black height of the root. Every remaining interior node, so remaining interior nodes has degree what? 2, 3 or 4. It cannot be more than 4 and it has to be at least 2. Everyone has that degree, every internal node. So either here it is 3, here it is 4, actually here it is 2. So remaining nodes degree has degree 2, 3 or 4. Okay, if this is true, then definitely this tree has to have at least how many nodes? It has a height of BH root and every node has at least 2 children. So it must have, so this tree, this contracted tree has greater than equal to how many? Total number of nodes? 2 to the power BH. 2 to the power BH root. Right? Because your first node must have at least 2. In the second level, all the nodes have at least 2. So it will be 2 to the power BH and your total number of basically height is B of H. Sorry, BH of root. So what does it mean? This means 2 to the power BH of root must be less than equal to total number of nodes I know in this tree. N, right? Or you can argue about the leaves. How many leaves does it have? Sorry, actually you should not have this 2 to the power BH root is the total number of leaves. At least this many leaves are present in this tree. And this 2 to the power BH of root must be less than equal to then n plus 1. And that immediately gives BH of root is less than equal to log of n plus 1. Now this is the black height of the original tree. So what is the maximum height of the original tree then? Twice of this. So the max height of the original tree is less than equal to 2 times BH of root, which is less than equal to, or yes, less than equal to 2 times log n plus 1. And that's the proof. It's a very simple proof, but you have to do, but the trick was to contract the tree. You just take out all the radius. Okay. So we know that if we can build a tree like this, then its height is good. It is log of n, order of log n. But it does not come automatically. You have to keep all this property to be valid all the time. All the 3 properties, they should not be violated. When you insert something, you have to keep track. You have to take care of all these 3 properties to be invariant over all your operations, insertion and deletion. So now you are gaining in search time, but you are losing probably in the insertion and deletion time, but not too much. But not too much. But every time you insert or delete, you pay something. Rather than paying a lot of things at some point of time later, we just pay a little bit every time. So that's the idea here. You pay a little bit every time, so that at some point of time in the future, you don't have to pay too much at one point of time. That's what it is doing. You're keeping this balance by this red-black thing. Every time you insert and delete, you do some bookkeeping. Not too much, but some, at least some. Previously, probably you are not doing anything, but at some point of time, probably you were paying a lot later. So that's the motto here. Now, before I go to how do we do this insertion and deletion, I need to define two operations which are called the rotations. Okay, this is a very important operation, and almost this operation will be used in almost any balanced binary search tree. To keep binary search tree balanced, this is the operation which is used in almost any tree, which is called rotations. A rotation is basically a restructuring operation, so that it improves the balance of the tree. So let me just pictorially tell you what does it mean. Okay, here is the operation. So we say if we are going from this configuration to this configuration, it is called, we are rotating y. This is a right rotation. We are rotating y in the right direction, and this is called the single rotation. Okay, I don't have to tell you what to do. So basically, you can see as if we are rotating this entire structure, y is going this way and x is coming up, and you are putting this b as the left subtree of y. See, by doing this, we don't disturb the binary search structure. Like right subtree of b can easily be put as the left subtree of y. It does not, because y is definitely larger than all this. Okay. And x is definitely smaller than all this. So I can safely do that. So this is called a right rotation, as if you are putting a fulcrum here and rotating this entire structure. Y it is rotated to the right and x is coming. So this direction, it is called single rotation right, single right rotation of y, and just the reverse operation will be a left rotation of y. Left rotation is as if you are rotating y in this direction. This is the structure. Rotation means if you have a structure, a node y, a node x, and this is the subtree I am drawing. A and B and C are the subtrees. By rotating to the right, it means this configuration becomes this configuration. As if y is going to the right and x is coming up. This entire thing as if it's rotating this direction. And just the opposite will be the left rotation.
Sir, why is it both the time rotation of y?
Because this is the definition. We cannot argue why some definition is something. This is the way we are defining it. Okay. So when we say rotation of y, right rotation of y, it means going from this configuration to this configuration. Left rotation of y, it means going from this direction to this configuration. Okay. So if I tell you to write the program for this left right rotation, you can immediately do it. Basically, it's just changing the pointers, changing a set of pointers, basically, nothing else. Just set this left child to be this, this parent to be this, all this. It's setting up pointers. It's a constant time affair to rotate a single node. I'm not going to write that part of the physical. I leave it to you. Now, this is a single rotation, but similarly, there is called a double rotation. So here is a double rotation. What is a double rotation? So let me again just tell you. by a picture. Okay, so this is a double rotation. So basically, if we go from this configuration to this configuration, no, this is X, this is Y. This is called a double rotation. Okay, you can see how the double rotation is performed. You are first doing a left rotation of Y. If you do a left rotation of Y, Y goes here, X basically come here with A and B to be the left and right child. Then do a right rotation of Y, then Y will come here and exactly this will happen. So this is a conjunction of two single rotations. So first this is a single left rotation of X according to our definition. Then you do a single right rotation of Y.
Single left rotation of Y.
Right. So single left rotation of Y, then you single right rotation of Y. Then you will get this, exactly this. So that's why it is called double. There are two single actually. Okay. So these operations you can see it tries to balance the weights. Suppose this part is too heavy, it's distributing over the two parts. That's why these rotations are carried out. But we will see how automatically this will be useful in our keeping the red black tree property.
Single right rotation of Z.
Single right rotation of Z. I can define this one also. Single left rotation of Y will be like this. Then you do a single right rotation of Y. Because single Z rotation will not. You will see you will not get this exactly this because single rotation does not define this configuration. This part of the configuration is not defined.
So but right and left rotation should cancel the effect.
No, it is not cancelling because you are not doing it exactly. So suppose if you do a left rotation, Y comes here. So let's see. Here left rotation of Y will bring Y in this direction. So Y will come here, X will have A and B to the left child, and Y will have the right child as C. Right? Then, oh sorry, then it should be single right rotation of Z. That's what you were point. Then it will be, so basically then you right rotate Z, then you will get exactly. Okay, so now we know how to what do we mean by this single rotation and double rotation. Now let us go to our insertion routine. Suppose how do we insert new elements into the red black tree and keep its structure as we define. All the three properties have to be valid all the time when we insert it. So the first thing, remember what is the insertion. First we find out the node to which it has to be attached. Find out the node. Basically it is the last node before the leaf according to our definition. The node which has both the children as empty or at least one child as empty. Okay, we always go to that node, then attach this new node. If that, I assume that has been done. After that, what do we do? So, suppose this is our node which we have reached. Okay, it has, I know it has at least one leaf. And we are going to put this new node which I am going to call as say X. So I am going to put this new node X So it will be inserted. So I will insert this one as x. Okay. And this one have both the children empty. You remember in the insertion of the binary search tree, that's what we do. We find out this node, then we insert on the proper place. So that proper place I am drawing it vertical. This can be left or right. I am not drawing it properly because I don't know whether it is left or right. But in the algorithm actually you will know whether it is left or right. Basically you just address that node x. That's what we do. Once we do this, now you see, I cannot keep this one as black. Because if I keep this one as black, it might have increased the black height of these leaves. Because there are other parts of the tree, there I didn't do anything. But those leaves also have the same black height as these leaves according to our method. So what do? We just make it red. So it does not increase any black height. There was already a black and that is already there. So I make this one as red. But the problem is, if I make this one as red, if this incoming edge was red, that will violate our red criteria. We have to take care of it. So let us see how do we take care of it. So let me just use some notation. I will be using new as x dot t. So basically this will be our new. Correct. Okay. So you will see probably we'll have to move up all the way up to the root. Probably. Every time we take care of all these three properties. And only violation will be this violation. If Q has a red incoming edge and a red outgoing edge, then this is the only violation. You cannot violate any other property of the red-black property. This is the only violation. So you have to write here, suppose this is red, incoming was red, you have to take care of it. So let's see how can we take care of this. Basically this is solved by case. There are several cases and we will take care of each case. So first, case 1. Incoming edge to new is black. What do we do? It's okay, it's done, we are done. We don't have to do anything. You remember? We made this one red and this one is black, or even in the generic state actually this new will be moving up actually. Suppose this is we have made this one is red. Okay. So we will have to probably move up, but at some point of time, suppose incoming is black, we are okay. There is no black red situation anymore. We are done. So in this case we stop. We are done. Okay. This is the case 1, which is a very easy case. Now case 2. Incoming is red. Incoming edge of new is red. Let set mu is equal to new. We have to look into the parent of new now. Okay. Let's see. Let's assume mu is equal to new dot p, the parent of new. Now we have several cases. So case 2.1. So this is the picture, several cases. So now suppose this is my mu, this is the new, and this one was red, this one was red. This is the situation. Okay. And case 1, see, this must have at least one right child. It cannot have without a right child. You find out why. Okay. If it has a right child, and suppose this is red, so that is case 2.1. So both, case 2.1 is both outgoing edges of mu are red. So this is the case. Mu is the parent of new and both outgoing edges are red. Then what we will do, we'll call this one as a promotion of basically mu. How do we promote? We promote its black height, increase its black height. We make these two red as black. Making it black does not cause a red problem. The problem, but it creates another problem. It may not keep the black height same over all the leaves. But see, I have a black here. I have a black here. Why it is black? Can somebody tell me? Because if this were already red, this cannot be red already, because already the tree was a red black tree. So this is a black. So I transfer this black to this one and make this, so this is transferred as, this one made red now, and this to black, and this one is red. It's okay. Transfer the red to here, and the black comes here. So black height does not increase over all the parents of this. Only its black height has increased, but all the others did not get disturbed by this operation. But at least what we have done, we have taken care of at least this nu. I have to take care of now mu. I have moved up.
New statement that you insert.
No, we have inserted the element, we are moving up. We are taking care and moving up the tree. I am showing a generic case now. Suppose you are taking care of the node nu, then what do you do in this case? I am showing that case. So now it has, now by this operation I have moved up to this node now. I have to take care of this node because I have made some black to red. That may cause a problem in the higher level. Okay, so I am showing a generic case. So this entire algorithm will move up the tree, and ultimately when it will reach the root, it will stop, because root cannot violate anything, because there is no parent of the root. Okay, so that's the strategy. So let me write this one, what I just said. Promote mu. Promote mu means, I already told you, if mu dot p not equal to nil, then you just update mu is equal to mu dot p. Now your node mu will be mu dot p and recurse. You recurse entire thing for nu. This is the case 2.1. Alright. Now let's look at case 2.2. What is the case? Only one child of mu is red, and let's assume that the left child of mu is red. Previously we assumed both child of mu is red. Whereas now we are assuming only one, and that is the left child. Suppose that's the case 2.2. So nu is the left child of mu, and left outgoing edge of nu is red. So this is the situation now. We have this node, we have, so this is nu, this is nu, this is red, it has this one which is black. This is red, this is some signal. Suppose there is a tree here, there is a tree here. So I am taking care of this person here. We are looking at parent. It has, again, one of the edge is red, and suppose this is the red. Because if it is not red, it's okay. Because we are taking care of it, nothing is violated. Suppose this is red, then what do? We just do a single rotation of mu to the right. So single rotate mu to right. So if you single rotate that way, it will be looking like this exactly. Sigma will come, you will come here, this will be here. Two will be there. Exactly, this is the situation. And if this is the situation, you can see, you verify, okay? So this configuration goes to this configuration by a single rotation. You have to go back to single rotation definition. And you will see, if we do this, now we are done. we don't have to go back anymore because we didn't have to do anything to the parent of this remaining black. So we are done. In this case, we don't have to go up. But one needs to verify all this very carefully. You go back home and verify all this carefully. Why it is okay. Okay, I'm just giving you the major ideas here. Okay, so this is case 2.2. There is a symmetric case where it is a right case. Like this is a left, this is a left. There is a symmetric case where this one is right, this one is also right, where both are right. And you just do the opposite rotation. So there is a symmetric right, and you do just a opposite rotation, left rotation, and this will be fine. There, here it is a left child which is red. This is also a left child. So this is the configuration. What I am saying, there is a symmetric case where nu has the right child which is red, and nu has an edge which is on the right side of it which is red. Instead of left, that is right. That you can also take care in a similar manner, only instead of right rotate you have to do a left rotate. Now case 2.3. So case 2.3 is nu is left child of nu and right outgoing edge of nu is red. Okay, so this is the situation now. So this is mu. So nu is the left child which is red. Now instead of left child of nu becoming red, its right child is now red. Yes, somebody said it very correctly. So this is the situation now. So now what you do, just double rotate. You just do double rotation, then you will see it will be perfect. So you just double rotate it, and if you do a double rotation, you will get this configuration. This will be nu, this will be rho, this will be mu. This will be red, this will be red. So double rotation. This is a and you can see now we are again done. It is perfect. I don't have to recurse up anymore. And see when I say this is perfect, basically you have to see two things. Your black height elsewhere is not disturbed, and red thing is not violated, and it is not violated, and your black height elsewhere is not disturbed by doing this operation. Okay. Similar to this, there is a symmetric. What is a symmetric case? Basically, there is a right-left combination. Here it is a left-right combination. There can be a right, and this one is left, right-left combination. But that also you can take care exactly similarly. Just double rotate. So there is a symmetric right-left case. So this is the entire operation. So these are the only cases. They are all cases we have taken care of. Now this entire operation of keeping this tree balanced, how much time is it taking? You are moving up the tree, and how many times you can move up? That's the height of the tree. Height of the tree is order log n, you already know, and each rotation at most takes constant time. So you can do all these operations in order log n time. So you can keep your tree balanced in order log n time for insertion. Now, you remember, not only we have to do insertion, but we also have to do deletion of nodes. Today we don't have the time for this deletion, because deletion will also have several cases. We have to handle case by case. So in the next lecture, what I will do, I will teach you how to take care of this red black property when you delete some node rather than insert. But I would encourage you to go back home and check how you yourself can come up with all the cases properly and take care of it. Again, you have to do it with left and right rotation, sometimes double rotation, and moving up the tree. Okay. So this tells you that you can always construct a binary search tree and keep it balanced all the time if you do some bookkeeping. And this red black tree actually is quite easily implementable. Okay. So in the next lecture we will see the deletion.